Okay, so we're going to be doing Atari 6502 assembly language programming today. We're using the Atari Roots book, so like we're on page 109. So like over here you can see Atari Roots. It's a guide to Atari assembly language. What did I say, 109? And the previous videos we've gone through all the other chapters. We kind of learned how to use the assembler, what bits and bytes are. A lot of boring stuff, and then we got into the CPU with the 65026 CPU, the registers, and we made a little program to add two numbers together. We learned some basic stuff like that. And you can always go back to the Atari 6502 playlist I have on YouTube to kind of like review that. And now, hopefully, we're going to learn a little bit about looping around and branching out. So these are like control flows within the language. Hey, Paolo, how are you? Let's see, do I need to say anything else before we get started? Yeah, so the Atari Roots book, in my other Atari videos, it has links to where you can find this material. We're using the Altira, the thing you see over here on the right. The Altira is a emulator for Atari computers. We're emulating Atari 800 XL with, I think, 64K of memory. And we are using the Mac 65 assembler. So we're actually typing it within an Atari rather than coming up with like Visual Studio, upload it to Altira and all that kind of stuff. So that's the setup, and let's just get to it, I guess. Hopefully I don't forget too much of what we were doing. All right, Chapter 7, Looping Around and Branching Out. Now we're going to start having some fun with Atari assembly language. I guess up until now it hasn't been that much fun, huh? No, I've actually enjoyed it. The first few chapters were really boring, to be honest. They were really boring. Felt like a history lesson and like really remedial math, but like whatever, we did it. In this chapter, you'll learn how to print messages on the screen, how to encode and decode ATASCII, Atari ASCII characters, and how to perform other neat tricks in assembly language. So ASCII is just like an encoding for characters. You probably have heard of it. Actually, I have no idea what it stands for. You think the A is American? Standard Character? Let's look up what ASCII is. That's so weird, right? Where's my browser? Here we go. Let's look up what ASCII stands for. American, I was right. American Standard Code for Information Interchange. Oh, I guess it was for information in general interchange. Kind of makes sense. It's characters, right? So that's cool. The Americans planted the flag on ASCII. Um, we're going to accomplish these feats with some advanced assembly language programming techniques that we haven't tried out so far. I'm not sure how advanced loops are, but yeah. Along with some new variations on techniques covered in earlier chapters. These are some of the programming techniques we're going to cover in this chapter. Using the assembly language .byte directive, incrementing and decrementing the X and Y registers, using comparison and branching instructions together, advanced looping and branching. Oh, I wonder what advanced looping means. Have you ever thought of like, oh, this is an advanced for loop. This is an advanced while loop. Like, it doesn't really make sense, right? Writing relocatable assembly language instructions. Ooh. Before we get started though, I'm going to pull a very sneaky trick. I'm going to ask you to type up and store on a disk a program that you haven't yet been introduced to. I ranted about this yesterday. I hate this. I hate it when they give you code and they say, "Don't worry, you don't have to understand this code. Just write it all up." And it's like, well, can't you sort of build up to it? I hate it. You probably won't understand it unless you've had some previous experience in assembly language programming. I'm asking you to type this program because it contains a couple of subroutines that are needed to run two other programs. Oh God, I'm going to have to type two other programs. Programs that will be introduced and explained in this chapter. The program you may not understand is one that will be explained in chapter 12. Oh my God, we're chapter 7. And they're going to explain the program they're asking me to type up in chapter 12. Okay, that's more than a sneaky trick. That's, you're being a bastard. IO and U. Two good reasons. There are two rather sophisticated but extremely useful subroutines in this program. One is a routine that will open your screen as an output device and put your Atari into its screen edit disk. Screen edit disk. You'll already have that job done the next time you encounter them in IO and U. So I hope you'll look ahead to greener pastures in the last chapter of this book and not be too angry at me for asking you to type this program. I'm totally angry at you. I'm so angry. And why can't you just make it print instead of print? Seriously, it's a label. All right, here we go, guys. We're going to have to type this. God, I hope I remember to save this. Let's check what out. Let me check what disk I have in here. Disk drives. Oh, I have no disks in here. So I like to show you guys when I set anything up like that. So let me switch to desktop mode. And let's see, we go to disk drives. We have nothing here. So we're going to try to load something. And this might be actually the right one, but let's see here. I have ROMs. No, it's one of these. God, I really should make a note which one I'm using. Mac 65 with DOS. I think what we want is the one with Bug 65. Yeah, let's make this disk number 1. And then so when I look into, how do you look in disk? Is it dir D? What? I can't remember any. No, it's list, right? List D1 colon. Oh dear God. This is what happens when you can't remember anything. We made a cheat sheet. Did we actually write anything down? We didn't say how to look up a program by typing dir. So shouldn't this be dir? Or are we not? Dir. Oh, what the hell? Didn't I type that before? All right, we only have one free sector here, so this is kind of like a bad disk to use for this, but maybe it's enough. Maybe we can make a new disk. So we'll do drives. Disk drives. Do you remember how to format a disk? Let's see if we can remember how to do that. Yeah, that's kind of annoying because, well, what we'll do is, I think I was using this roots ATR disk. How do I switch to D2? Is it just this? Come on. Dir D2? Dir D2? Seriously? This is one of those things that I just feel like I hate using AI, but it's just a lot easier. Maybe to ask it. No, we don't want this one. What's a decent LLM? Gemini. Now you'll see all my other queries. Alright, so how do I run dir on D2 using Atari OS2A? Is that what it's called? OSA plus. Type D2 then colon. Isn't that, did I not do that? Doesn't work. Is it because I don't have a D2? No, I do have a D2. There's something very funny going on. This is why I always have a problem. Did I not start this stream saying like, hey, I can never figure out. I always get stuck when there's a problem. System enter. I don't think that is what we need to do. What a pain. All right, we're just going to ignore it. We're just going to continue. We'll figure this out next time. Let's go back to Atari roots. That's not good. Here we go. Why are you guys not seeing the same directory? Do I have two Altiras up? One second, this is really confusing me now. Atari. Altira's here. There's two Altiras somehow. Aha! Maybe you guys haven't been seeing what's going on. Maybe this is why it's not working right. Let me just restart Altira. Okay, so we're here. We have disk 1, drives. We have 2 virtual drives. Now if I do D2, it still doesn't like it. Anyway, we'll just try and hope that we can save it in this drive. Max 65420. Oh, we're really screwed. It's like not even... I bet it's because I'm rebooting and BASIC is on. Let's fix this. I bet this is it. This has to be it. File. It's under File. Where am I not seeing it? It's not here. System. System, configure system. And under here, disable internal BASIC. Enable basic boot without options. So we don't want this. We close that off. And now we restart. Aha, look at this. It says D1. I knew it looked weird, right? Oh my God. Hold on. I got to really put this in the browser so that we don't get, I think I probably already have this in the browser actually, but let's check. Yeah, this one over here. Debugging. Something not working. Make sure that la 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 make sure basic loading is disabled by default. There we go. Make sure DOS Excel disk is in D1. Alright, so looks like I got hosed by this once before because I put it all in caps. So I've called out the section here called debugging when something's wrong. Hopefully we won't get into this trouble again. What a mess, seriously. Okay, so now I can do D2. I can see what's in D2, and now we have plenty of space in D2. This is where we're going to save our data. All right, so let's go ahead and type this program in. So we're going to go back into D1. We see there is max 65420. We run that. Now this is our assembler, and this is where we're going to type our code. So we'll type it in pretty much exactly as they have it. Title, print screen routine. 30 dot page routines for printing. Sorry, they're not overlay. Printing on the screen. Uh-oh, I screwed up. The 20 needs 2 spaces because it is, it's only 1 space for the remark, but for the print screen routine, for compiler, for assembler directives, we need to put 2 spaces, so I'm going to have to retype these. Routines for printing on the screen. All right, so we have that now. We're at 40. 50. 2 spaces because this is a directive. This is saying we're going to start the program in memory address 5000 hexadecimal. 60. Comment. 70. Buff len equals 23. It looks like this is on the first. This looks like it's on the first character, so it's not a compiler directive. 100 EOL is equal to $9B. $sign just means hexadecimal. $105 comment. 110. Now, oh, these are all 1 space. I hope later it's not, right? Yeah, here it's 2 spaces because these are actual operations. Okay, so where are we? 110 open is equal to $03. 120 O write is equal to $08. 130, put character is equal to $0B. 135, section. 140, IOCB2, whatever that means, equals $20. 170, we're skipping a whole bunch. ICCOM is equal to $342. 180, and if you see me type anything wrong, please tell me. IC ball is equal to $344. 190, IC BAH, BAH, is equal to $345. 200, ICBLL, is equal to $348. 210, ICBLH, is equal to $349. 220, ICAX1, is equal to $34A. I should just say hex 34A, right? 230, ICAX2 is equal to hex 34B. 235, new section. 240, CIOV is equal to hex E456. 250, new section. 260, screen name dot byte E colon, that's a comma, EOL. 270, new section. 280, last one, OCSR, O screen, I guess. Open screen routine. Ah, that's the label. Open screen. O means open. All right. Now we have some code that starts. Load the X register with IOCB2. IOCB2. So we're putting in that number directly, which is 20, right? 300. Load the accumulator with open, and that's 3. 310. Store the accumulator to this address, icom mine, comma x. X is probably 0. No, x is B2, 20. So it's going to take the icom address 342 and jump, add 20 to it. 320, new section. 330, load the accumulator with screen name ampersand 255. I don't know what that does. 340, store accumulator IC ball X. So we're loading whatever this screen name thing is. Maybe this is a bit flag, right? This is probably a bit flag. And then we're putting it into this address. IC ball X 340, 350. Load accumulator with the number screen name 256 divided by 256. I'm sure that's not really divided by. 360 store accumulator into so what we can see here is there's a lot of like all the numbers, like whenever we want to move it from a memory address to another one, we kind of have to go through the accumulator, which is kind of interesting, right? It's like we can't just say like, hey, take memory address 20 and put it in memory address 40. Like we have to be like, load memory address 20 into accumulator, store accumulator into 40. 360 store. 370 is a new section. 380 is, oh god, I hope I've remembered to save this. Right. We're loading the accumulator. 390, now we're storing again, of course. We're just moving stuff around. 400, now we're loading the accumulator with 0. And we're going to store that 0 into icax2.x. I'm sure surprised there's no way to just store a literal number. 420 jump subroutine CIOV. 430 new section. Oh, good, they tell us now save it, we'll remember. 440 load accumulator with put char. 450 store accumulator into ICCOM X. 460 new section. 470 load accumulator with text buff and 255. 480 store accumulator into IC ball X. 490 load accumulator with text buff slash 255. 500 store accumulator to ICBAH comma X. 510 return to subroutine. 520 new section. 530 label PRNT. 540 load the X register with IOC B2. 550 load the accumulator with buff len and 255. 560 store ICBLL comma X. 570 load accumulator buff len slash 256. Oh guys, I typed David, I'll look at what you said in just a second, but I noticed I made a typo in line 490. This should say divide by 256, so I'm going to do that again. 490, load accumulator text buff 490 slash 256. Okay, 502 is wrong, it's 520. You're right. How do I get, well, 502 doesn't hurt, but you're right that we need a 520. I don't know how you delete like a line. How do you remove a line? Do you just do 502 like this? So what'd you say earlier? Trying to learn as we go. Is there a reason we skipped over 150 and 160? No, this is code like that they said, you know, we're asking you to type it in, we'll explain it later. But I'm guessing either that when they wrote it, they thought they might need more stuff. So what are you looking at? 150. I don't think there's necessarily a reason, or maybe later when we use this, they're going to add some more stuff in between. So no idea. they kind of asked us to write this code without. Were you here when we started? They said something like, I'm going to pull a very sneaky trick. I'm going to ask you to type up and store on a disk a program you haven't yet been introduced to. And then they said, don't be so mad. Don't be too angry at me. So we're trying not to be angry. I was angry, but we're almost done. So what are we at? 570 here. Now we're doing assembly, Atari assembly, in case that wasn't clear. 570. So the next one's 580. Store accumulator to ICBLH, X. 590 is jump subroutine CIOV. 600 is return to subroutine. 610, new section. 620 is text buff is equal to star. This is a label. It looks like, I don't know, maybe 630, new section. 640 star plus bufflen. 650 660 dot end. Oops, 640 I did wrong. It should have been 2 spaces. No, that is 2 spaces. I did it right. So let's save it first. So we'll do list is to print it. God, I almost removed my program. List D2 to save it in drive 2. And what did they call it? Maybe it's print SC. Here it is. Print SC. PRNTSC dot source. We'll save it as a source file here. List will print, yes. Okay. So now we will just list it on the screen and make sure it looks right. And let's try to assemble it. See if it fails. Alright, it seems to have worked. You can assemble its object code and save it on disk under print screen object. I forget how to do that. I think that was with bsave, or is it just save? 1 second. So there was bsave differences, max 65, bsave instead of save. Bsave, blah, 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 replace start and end, bload. So what does just save do? That's what I don't understand. Bufflen, COV. See, I don't know what the end of the file is. Damn it. Let me try typing that again. Maybe it'll tell us. 5,000 symbols. Bufflen. Bufflen is the first. Yeah, this is Bufflen is where it starts at 17. And then print is one of our labels, right? Yeah, that was not the end of the program. Well, we don't really know how to save it. Maybe save just does it. No, doesn't matter. We've assembled it. We're okay, I think. Then there's another program I'd like you to type and assemble. It's the one we're going to be working with for the rest of the chapter. Okay. So I think if we go back here to CP, we should see our code in D2. We have print screen. So if I go back to the editor, Max65420, and I list, I see nothing, then I can do enter D2 print screen dot source. Is that not what it was called? Print, oh, SC, print SC. So let's go back. Enter D2 print SC dot source. This should I can almost type prntsc dot src. There we go. It loaded. Now if I type list, there's our code. And if I assemble, it assembles it here. Okay. Now we have to type in this one. So we're going to type new so that we have the new code. And we're going to type this. 20, the visitor. 30, 40, no, 35. Text buff is equal to $5041. 40 open screen is, oh God, open SCR. I'm sure I must have made an error in the other code because I just make so many typos. Print, see, like that. Print line is equal to $5031. 70, 80. This is telling it where the program starts in memory address hexadecimal 600. 90 is a new section. 100 text. Is this one space, right? Yeah, that's one space. Text is a label. Dot byte. $54, well, hex 54, hex 51, hex 4B, hex 45, 4B, 4520, 4D, 4520, 2 spaces byte, hex 54, hex 4F, hex 20, hex 59, hex 4F, hex 55, hex 52, hex 20. Line 40 is misspelled. Open SCR 5003. It looks right to me. Maybe this was while I was misspelling it? Or you mean in my previous code? 120 byte 4C 45 41 44 45 52 21. 130, 140, Visitor. Oh my God, why are we so leet? 160, load the X register with the literal 0. 170, this is loop is the name of the label. It's not a keyword. Load accumulator text comma X. So it's probably going to look at this text section here and start with the first byte, which will be 0, which is 54. 180 store into text buff comma X. Store accumulator, the value I don't know what that is. Store into that address, right? Oh, text buff is here, 5041, but offset by X. Okay, so we're just basically doing a copy by loading this section here, and text buff is where we're writing to. Then we increment the X register. SRC. Oh! Ha! Sorry, you're absolutely right. SCR equals 5003. Thank you so much. I think I'm dyslexic, honestly. But not so dyslexic that it was so obvious. CPX23. Compare with the X register 23. I think. If it's not equal, branch not equal to loop. So as long as it's not the number 23, just keep going, I guess. I see, because X is basically going to increment. These are probably 23 letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yeah, that's why it says 23 here. We're just basically incrementing, so it's a for loop from 0 to 23. Or 0 to 22, really. Branch not equal loop, so it'll just keep looping until it's X does 23 times. And otherwise, we jump subroutine open SCR. Jump subroutine PRNTLN. Ah, these addresses are subroutines, and probably we filled these addresses in this code, 5003. Yeah, because you see, like, it can calculate based off the 5000 here. And it probably knows, like, hey, if we're starting at 5000, then this open screen routine must be 5003. Because this is, yeah, I'm guessing. It's funny how they have to do this manual addition, and print line is going to be 5031, and print line is here 5031. Wait, print line 5031. It's probably this, even though it's not that same name, right? Because here's open screen, and here's print. All right. Anyway, infin jump infin. Infinity, this is the label infinity. Jump infinity, which means just keep looping forever here, because it's just going to jump back to itself. This program is called for reasons you'll soon discover the visitor. It's a program designed to print a cryptic message on your video screen. Well, let's save it first before we lose this. And saving it is list drive 2. And they called it like VizTor, right? Let's see if we can assemble this. Does it work? Oh, undefined label. Undefined label. How do... I don't know how to see the... How do you go up? How can I see what it was? Like, it just scrolled off. Oh my god, I don't know how to do this. I can probably look at the undefined label. Oh god. So it's probably right before print line. Right here, right? GSR print line. Let's see here. Let's do a list again. JSR open screen print line. BNE loop. This is loop. Open screen. 40. There, what is, can you do it like this? I wonder how to give it a list. In Max 65 for Atari assembly, how do I list a range? How do I use list with a range of line numbers? Comma. List 10, comma 40. All right. So what was it here? Loop. Where's the others? Dot, 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 dot. All right, so we're using BNE loop. Loop's right here, so I can see that's correct. Oh, I typed open screen wrong again. David, you're so good. I'm the worst at this, right? This is why I need a real compiler, I think. Did I do something else again? Is this what it means, like with the question mark maybe? It doesn't know what that means. Open scr. Open source. Just kill me. Just kill me. There we go. All right, so we saved VizTor. You can run it immediately, just assemble it. The problem is we first need to assemble the previous one, so we have to load that. So we do enter D2. What's it called? What was the previous one? Print source list. We assemble this. Okay, so now all of this is in memory. And I think we already, I think the other one is there too. So visitor dot source should also be here. The visitor, and then we can assemble this too, and it's in memory also. When you have the program typed, you can assemble the object code and save it on disk under print screen.obj. Then there's one program I'd like you to type. Wait, oh, we did that. Yeah, we did this already. When you finish typing the visitor, you can run it immediately. Just assemble and load the object code into your computer. Then you can run the visitor either by putting your computer into debug mode and typing G617, or by getting into DOS mode and running the visitor with a DOS command. Visitor.source. Why is it an S here now? Anyway, after you've run and saved the program, you know exactly what it does. So now we can explain how it does what it has done. Let's try running it. So we go back here, and then we run our debugger, bug65. Oh, you guys don't hear the sounds, right? Now? Now you hear the sound, right? Right, it said to run G617. I have no idea what it did. It didn't do anything for me. That was lame. Here, let's try running it in DOS. 1 second. How do we run in DOS? Oh, you guys didn't see my, I left the browser on. Yeah, well, we want the browser now, actually. The browser we had, how to run from DOS. Here. D1 run. So we just type in run 0617. I think it was 17, right? Yeah, 617. So let's see if this one works better. Does nothing. I feel very ripped off. It probably should have done something. I don't know. Let's figure out how to save it as an object file, but I don't think I did anything wrong here. Life is hard. So we're going to load visitor. What, visitor.source I called it? No, it's D2. This program begins on line 5000. EOL 9B, bufflen 23. So the first thing here is skr name. So when I assemble this, visitor, Something seems weird here, right? Because it has our old code here. Let me do a hard reset of the computer. There we go. And we'll do max65 here. So we'll kind of do it from scratch. Enter d2 visitor.source. We have the source now, and now, oh no, I should have, it's the other program. max65420, enter d2, what was it called, open screen? Print screen. Print screen dot source. We list it. We assemble it. This is all the code that gets assembled. The symbols are here, so text buff equals da 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 buff len. Print, here's print 5031. And here's open screen. Where's open screen here? 5003. That was the same code that we saw here, right? 5003, and print line should be 5031, 5031. So they match up here. The numbers match up, so that's good. The only problem with saving is when you save, you're supposed to know the last memory address of the program, but I don't know it by looking here. Well, anyway, let us now try loading visitor, because this should be loaded in memory. Alright, so now both of these are in memory. I go back here. Now when I run bug65, I should see code at 50050, what was it, 31 or something? What 5003. There should be code there. Oh no, it's totally empty, which means that when we've loaded the second program, it wiped the first. I see. So we've erased the program. But here we should be fine. Let's look at print 600. This is all empty too. How come all of our code just like isn't loaded once I'm in here? Like nothing's in memory. Did I type in 600 wrong in the source code? No, it says 0600, which is basically the same thing, right? Yeah, it makes no difference. Yeah, it's the same thing. So when I assemble this, this code should be let's see. It says Bister is in 617 and text is at 600. So we should at least see something in 617 where the code starts. So let's print 617. I don't understand what's going on. 617. We're totally empty. I know what's going on. I remember that for Mac 65, we have to give it a compiler directive called opt obj. Otherwise, it won't load the memory. It won't load the assembled stuff into memory. God, why? Why would they? Why would they not remind us of this? So, hey there, Mabel and Krisky. Like, we're not doing basic, we're doing 6502 assembly programming. So what I'm going to do is make sure I don't make the same mistake again in the future by adding this into our debugging section here. Make sure to add .opt .obj, I forget what it's called, directive, whatever that, yeah. All right, so when we look at for opt, you need opt obj. It's opt space obj. All right, so let's go ahead and edit our programs to have that. So Mac 65420. We'll first load the first one. Which was it? It was called print screen.source. And in here, print screen.source. We want to put it right before this. So 45 dot opt obj. There we go. Let's see if this compiles. Perfect. All right, that's great. Yeah, and now I can save this. So list D2, and this is called print scr. I guess I'll make it a 1 maybe. I hope it can add a letter to it. Okay, so it saved that. And now let's load vistor.source. Let's list this. And we see 80, we have it. So right before 80, we'll add in a .opt obj. We'll try to compile this. It's all happy, and now we can save this. This is list d2 vistor2.source. And now we go back here and we go to bug 65. Now when I list 600, yes, we actually see, here's take me. You see, like, this is going to be, we actually did this kind of once before. Actually, we figured out on our own how to make this program work. A different program, right? Now that you mention it, it does read more like assembly. Yeah, it doesn't have, it has a lot of 3-letter things like compare X register, branch not equal, jump subroutine, right? So anyway, let's try to run this thing. G17 Take me to your leader. Look at that. It printed it to its screen, and probably it's gone into that infinite jump loop at the end. You see here? Infin, jump, infin. So, thank God we got that working. You know that it took us over an hour to do this? Yeah, it wouldn't be a bad idea to save it too on the disk, and I saved it already. Um, after you've run and saved the program, you'll know exactly what it does. So now we can explain how it does what it has done. We'll start with an explanation of the assembly language .byte directive, which you'll see in lines 10 to 120. So maybe it's good to load this program up in here so that we can see it. Enter the visitor2.source. And we'll do a list 100 to 120. There we go. So we see these commands. This text here is a label. So it just means we can reference this later. And then everything else here are just byte commands with a bunch of hexadecimal numbers. Looks like nibbles, right? So, which is what? 4 bytes, right? 4 bits? Anyway, look at this picture. I like kind of old drawings. It reminds me of like old D&D books. There's a little spider here. Looks like some sort of like inspector from like Pink Panther or Inspector Gadget or something. And here's like Elvira from like Addams Family. Is that her name? I don't even know. The byte directive. The byte directive is sometimes called a pseudo operation code or pseudo-op. I would have just called it pseudop. Wouldn't that be easier? Pseudop. Because it appears in the opcode column of the assembly language source code listing, but is not actually a part of the 6502 assembly language instruction set. Instead, it's a specialized directive designed that this is weird English. Instead, it's a specialized directive designed that can be used with some assemblers but not with others. I'm like getting stuck on the English here. Anyway, for example, .byte works with both the Mac65 assembler and the Atari assembler editor, but it does not work with the Atari macro assembler and text editor. Luckily, we're not using that one, huh? When you write a program with the Atari macro assembler and text editor, you have to use the letters DB in place of the .byte directive. Other pseudo-ops also differ from assembler to assembler. There are no generally accepted standards for writing pseudo-op directives, so pseudo-op codes designed for one assembler often won't work with another. Well, luckily for us, it works for both of them. Hey, why does this cut off now? Guys, when did this go bad? Let's see. So strange. I want it to be around like this, but somehow it's cutting off at the edge here. So let's open this up. And then we can make it a little smaller. And then we can make this one a little bigger. Alright, I have no idea when that happened, but it'll be a mystery forever and ever. What the byte directive does. When the .byte directive is used in a program created with the Mac65 assembler or the Atari assembler editor, The bytes that follow the directive are assembled into consecutive locations in RAM. In the program called the visitor, the bytes that follow the label text are ASCII, Atari ASCII codes for a series of text characters. All right, that makes sense. I'm just like so stuck on this here. So a two character hexadecimal. So a single hexadecimal can go up to 16, right? And to do 16 in binary, you need, well, it can go up to 15, right? And to do 15 in binary, you need 4 bits, is that right? So you have 1, 2, 4, 8. Yeah. So that is four bits for 1. So 2 would basically give you, 2, this would be 8 bits then, right? So each one of these here in hexadecimal is 8 bits then, right? So this represents an 8-bit. Oh yeah, I mean, God, I should just read, right? It says byte, so it's an array of bytes. It's a list of bytes. And I'm here like trying to do stupid math, right? 4 bits are a nibble, yeah. But here we're this thing with 2 of these is a whole 8-bit, and if it were just 1, then it would be a nibble, right? So okay, that makes sense. Sorry I blanked out there. Sometimes that happens. Sometimes the brain just stops working. It's like, what are you talking about? Math. We need more coffee. It's like, it's almost 8 p.m. and I'm not awake yet. Braining is so hard. It's a wonder I'm functional in the world. Looping the loop. Well, that sounds like a special, like, advanced maneuver. As we explained in Chapter 6, the X and Y registers in the 6502 chip can be progressively incremented and decremented during loops in a program. Yes, we saw Dec X and Inc X, or Inc Y and Dec Y, so we know how to do that. In the visitor program, the X register is increment. Okay, so I'm the brain's starting to brain. So this guy's the visitor. He's visiting. And he's saying, take me to your leader. That's why I said, take me to your leader, right? That seems kind of sexist. It's like, what? He saw a woman and was like, hey, you can't be the leader? The fuck? Push as fuck. Oh, God. All right. All right. Let's get back to business. All right, in the visitor program, the X register is incremented from 0 to 23 in a loop in which the characters in a text string are read. The characters that are to be read are written as ASCII codes in lines 100 to 120. So here, each one of these 54, 41 represent take me to your leader. So, yeah, that makes sense. Let's see here. So this 54 should be a T, right? The 54 should be a T. So let's look up ASCII chart with hex. And so we have a T54. Look at that. Hexadecimal 54. And then the next one should be A41. 41 hexadecimal A. There we go. Take me to your leader. We'll have to believe that the rest is actually correct. It is an exercise left to the reader, but we've proven it. We wrote the code. Okay. So when we say we're looping in line 160, let's go look at the program again so that we can see what it looks like. Here's the loop. So the loop starts here. We set the X register as 0. Then we load the accumulator with from the text address, but offset by whatever's in the X register. Then we store that in the text buff location, offset by X, and then we increment X and we copy X. No, oh, we compare, not copy. Compare X with 23. And if it's not, yeah, so we're basically looping until we see 23. Compare the X register with 23. So here we go, incremented from 0 to 23. That's what that compare X to 23 is about. The characters that are read are written as ASCII codes. In line 160, the statement load X number 0. This is number means immediate, I think. So it's just literally the number. It's not an address. Is used to load the X register with a 0. Then in line 170, the loop begins. Yeah, because it says loop here. Incrementing the X register. The first statement in the loop is load accumulator text comma X. Each time the loop cycles, this statement will use indexed addressing to load the accumulator with an ASCII code for a text character. There's a fun thing with increment X and decrement X. They set the 0 flag. So if you make sure the end of the loop is 0, you don't need to compare X. Look at you. So basically, it's sometimes better to count down rather than to count up. That's really what it means, right? Because counting negative to 0 doesn't make too much sense. I guess it could be done. All right. When the loop ends, all the characters in the text buffer will be printed on the screen the first time the program hits line 170. There will be a 0 in the X register since the 0 has just been loaded into the X register in the previous line. So the first time the program encounters the statement load text comma X, it loads the accumulator with a hexadecimal number 54. That's this 54 here. Hey Akram203_RR, welcome. We're doing Atari assembly programming. This is chapter 7, I think, in Atari roots. So we're kind of doing loops and branches, conditional logic. What programmers sometimes call the 0th byte after the label text. There's no need for a number symbol in front of the number 54. Incidentally, since numbers that follow the byte directive are always interpreted by the Mac65 and Atari assembler editor as literal numbers. All right, so they're kind of exceptions. Bytes cannot be dereferenced in memory, so they're always assumed to be direct numbers or literal numbers. How do they say it? Literal numbers, yeah. Hey, Blocks Hub Roblox, welcome. Welcome back. It's like the gang. I'm doing pretty well. I was saying earlier that I was so tired because I stopped taking my ADHD meds. I didn't say why I stopped taking it. I stopped taking it because I started getting little twitches, I don't know, my shoulder or whatever. And I was like, this is really bad. I was kind of freaking out. So I was talking to my psychiatrist and I was like, hey, I'm starting to twitch. And she's like, yeah. I'm like, well, that's bad, right? And she's like, well, I'm like, you know what? She's like, it's all right. I'm like, it's not all right. So anyway, long story short, I'm stopping most of my medication to kind of just figure out which one's causing the twitch. But it's really annoying. You asked how I was doing. people ask an autistic person how they're doing, they get a real answer. I'm doing great. Like, the weather's been good. Food's been good. I don't know. What do people say? I listen to some music. It's all good. My sports team won. I don't even know what sports are playing right now. It's winter, right? There must be like hockey. And what's in Europe? It wouldn't be football, right? No football right now. It's too cold. Rugby? Yeah, that's about it. Tennis? No, there's no tennis. I don't know. Maybe it's sports break for the winter. All right. Well, if people in chat know more about sports than me, you can certainly tell me what sports are being played right now. Okay, so where were we? Incrementing and decrementing the X and Y registers. Now let's move on to 190. Where's 190? Increment X. Means increment the X register. Since the X register currently holds a 0, this instruction will now increment that 0 to a 1. Next, in line 200, we see the instruction compare X number 23. That means compare the value in the X register to the literal number 23. The reason we want this comparison to be performed is so we can determine whether 23 characters have been printed on the screen yet. There are 23 characters in the text string that we are printing, and when we've printed them all, we'll want to print a carriage return and end our program. I'm guessing the 52 here is a carriage return? No, the 21 must be a carriage return. I didn't see that. The 21. Right, 21's carriage return. That would be decimal, right? No. Hex? Was it in hex? Where was it? No, it's hex. Hex 21. So that would be over here. Oh. 21. Whoops. Why is it not carriage return? It's probably a task key's different, huh? 33. Where's carriage return? 13. Let's look up a task key. Okay, so this is just to take me to your leader exclamation point. Where's the carriage return? Load, compare 23. Jump subroutine print line. I bet print line does the carriage return. Right? Bye, Unlink. Oh, no, it's not Unlink. It's SXodicas has to go. Unlink's like, I have no idea what sports are being played. No, 20's 20? No, 19 would be the new line, no? Well, I don't know. But this 21 here is the, do you see it? Is it being highlighted? Yeah. This 20 on line 110 at, oh, the 21 is the exclamation point. So this is like, take me to your leader, and it needs a new line. But I bet it's in print screen. Here, let's take a look. You're not stupid. Did you see what kind of things I've been saying? Let's look up the code for print screen. Because after this is done, you see it goes to print screen, right? Or open screen and then print line. So let's look up that. Open screen print line, that is 531. So here's open screen, da 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 da. This doesn't look like it's doing anything to do a. This looks like store line, maybe. I bet in here somewhere is doing a new line, but I'm sure we'll run into it soon. They're explaining this, and they're explaining it like in a lot of detail. So I'm sure in chapter 12 they'll talk about it. All right. We did this. Then we'll want to print a character return. Comparing values in assembly language. There are three comparison instructions in 6502 assembly language: CMP, CPX, and CPY. CMP means compared to a value in the accumulator. So you can only compare a value, like the parameter that's passed to CMP, with what's in the accumulator. When the instruction CMP is used, followed by an operand, the value expressed by the operand is subtracted from the value in the accumulator. This subtraction operation, so wait, it's the operand is subtracted from the accumulator. So it's accumulator minus operand. Okay. A minus O. AO. The subtraction operation is not performed to determine the exact difference between these two values, but merely to test whether or not they are equal, and if they are not equal, determine which one is larger than the other. If the value in the accumulator is equal to the tested value, the zero flag of the processor status P register will be set to 1. If the value in the accumulator is not equal to the tested value, the Z flag will be left in a clear state. If the value in the accumulator is less than the tested value, then the carry flag of the P register will be left in the cleared state. Oops, sorry. Okay, so if it's less than, then the carry flag is clear, because it didn't need to do any borrowing to subtract, right? So you do 5 minus 1, it's 4. There was no carry being used for it. If the value in the accumulator is greater than or equal to the tested value, then the Z flag will be set to 1 and the carry flag will also be set. This seems false. If the value in the accumulator is greater than or equal to the tested value, then the Z flag will be set to 1. Ah, yeah, that part's true. And the carry flag will also be set. So if they're the same, then the carry flag is going to be set. All right, I believe it. CPX and CPY works exactly like CMP, except that they are used to compare the values with the contents of the X and Y registers. They have the same effects that the CMP has on status flags of the P register. So I assume it's basically comparing it with the X, so it's like accumulator minus, no, it's X minus the number. So it replaces the accumulator. Seems like a pretty good book. Yeah, it's like really made for people who don't know programming and also don't know anything about the 6502 assembler language and know nothing about, like, yeah, just about nothing. So what's good for us is, because I know nothing about Atari, it kind of really like is gentle about what it expects you to know, even though I still had lots of problems just knowing how to like copy a disk, or because I just don't know these things. But in general, it's been good, because the other books are like, you get a 6502 book, it'll assume you know how to use, like, each computer is different, right? So here it tells you here's how to do it with your assembler, your macro 65 assembler or the Atari assembler. So that's kind of nice. Yeah, so, you know, maybe there's a better book for you, but this kind of just makes zero assumptions. The bad part about this book is, like, God, you see how slow they go through stuff? But, you know, that's okay. We're just here for chill vibes anyway. We'll eventually get there, just slower. All right, using comparison and branching instructions together. The three comparison instructions in Atari assembly language are usually used in conjunction with 8 other assembly language instructions. Wow, that's a lot. the 8 conditional branching instructions that we mentioned in Chapter 6. The sample program that we have called the visitor contains a conditional branching instruction in line 210. So let's see line 210. What does it say? BNE loop. So branch if not equal to the label loop, which is line 170. That instruction is BNE loop, which means branch to the statement labeled loop if the 0 flag of the processor status register is set. I'll say branch not equal. It's so much faster. This instruction uses what can be confusing convention of the 6502 chip. In the 6502's processor register status registers, the 0 flag is set equals 1 if the result of an operation that has just been performed is 0. And the 0 flag is cleared equals 0 if the result of the operation that has just been performed is not 0. Yeah, but if you think of the command as branch if not equal, then you don't have any of these like confusing like what to do with the Z flag. I just don't care. It doesn't really matter. It really doesn't matter. That's what I was just saying. This is all quite academic, however. As far as the result of the statement BNE loop is concerned, when your computer encounters line 10, it will keep branching back to line 170, the line labeled loop, as long as the value of the X register has not yet been decremented to 0. What? Have they gone insane? Do you guys see the problem here? I'm so confused. It's saying that we're decrementing has not been decremented to 0, the X register, right? But here, we're incrementing the X register. Once the value of the X register has been decremented to 0, the statement in 210 will be ignored and the program will go to line 220. Guys, am I insane here? Where are we decrementing the X register? This is crazy. I think they're just wrong. Anyway, let's assume it'll loop to 0. Yeah, it'll eventually loop to 0, but that's not what's happening. It's comparing it with the number 23. So increment x is going to keep getting bigger one by one until it gets to the number 23. And then we subtract what's in the X register, which is 23 minus 23, which sets the 0 flag. Maybe what they're trying to say is that once the comparison is 0, or the status flag is set. Yeah, that's crazy, right? Do you think I should write to the editor? All right. Yeah, we can be pedantic. In line 220, the program will jump to the subroutine open screen, right here, open screen, which currently resides in RAM beginning at the memory address 5041, provided the object code for both printsker and visitor have been loaded into your computer and are ready to run. That was the other program we compiled beforehand, and it just knows that the subroutine's in that memory location. If you don't know why and you'd like me to explain, please let me know. Yeah, tell them. I'm gonna write an email. Conditional branching instructions. Uh-oh, this looks boring. Boring as fuck. All right, let's just get through it, all right? We can do this. As we pointed out in the previous chapter, there are 8 conditional branching instructions in the 6502 assembly language. They all begin with the letter B, and they're also called relative addressing or branching instructions. I think I'll call them branching instructions because they start with B, right? These 8 instructions and their meaning are BCC, blind copy. Branch if the carry flag of the processor status P register is clear. If the carry flag is set, the operation will have no effect. Do you guys remember what the processor status register is? Maybe we should look at it real quick so we can remember it. Yeah, it's just a register filled with flags. But I think, did I put it in my gist? Let me see. Just give me 1 second here. Here's my gist. Where did I put it? It would probably be under maybe general. Nope. No, we didn't put it in here. But let's look it up because I think it's gonna matter one day for us. It's inside the 6502 page 43, which isn't exactly here, but it'll be close. Here it is. Oh, you guys don't see it. There we go. All right. X register, Y register, blah, blah, blah. Processor, here we go. Layout of this register, here it is. And then they print it out. I think where's just a summary here. 4 of the status bits are called status flags. They are the carry flag. Well, is there something that shows this better? Okay, so here is all the registers and stuff. So here's the X register, the Y register, the accumulator, and the processor status register, the program counter, I think it's called. I forget what SP is. Damn it. I almost remembered it all, right? And then in here you see the processor register are just flags. So it uses, instead of a number, like these just hold one number, this has 8 different bits. 1, 2, 3, 4, 5, 6, 7, 8. But it looks like one of them isn't used, so it means there's 7 bits being used. And let's see what they are. Oh, its stack pointer was the SP. I forgot about that one. We haven't really used that yet. I'm like going all over the place. 4 of the 5, where does it say this? It isn't used for storing. These 4 flags, 3 of the P other bits called condition flags. So let's see if we can like just copy this. It's like PDF, so I don't know if it'll actually copy, but let's see. And then we can just post it in here under, maybe we'll do it under 65026. We'll make something called 6502 CPU, and we'll do this. There we go. So we'll call this the P register. There we go. So now next time, if we ever need it, we can look it up pretty easily. All right, where were we? We're on page 117. Okay. Branch if the carry flag of the processor status P register is clear. If the carry flag is set, the operation will have no effect. Branch if the carry flag is set. So this is just the opposite. So it's really not like that different. Branch if the result of an operation is 0, BEQ, if the 0 flag is set. BMI, body mass index. Branch on minus if an operation results in a set negative N flag. BNE, if branch if not equal to 0, if the 0 flag isn't set. BPL, branch on plus if the operation results in a cleared negative flag. BVC, branch if overflow flag is clear. BVS, branch if overflow flag is set. What's the difference between overflow and carry? That's something we have to figure out. They sound like the same thing to me. All right. How conditional branching instructions are used. Oh, now I'm getting hot again. Wow, you know, it used to be that I would have more people on YouTube than on Twitch. And I thought, no way anyone's going to be interested in this on Twitch. Like, Twitch is like, you know, everyone's watching video games like Valorant or whatever, right? But now I mean, it's not a big number, 5 versus 1 on YouTube, right? It's kind of interesting how that can happen. All right, to use a conditional branching instruction in the IN6502 assembly language, the usual method is to load the X or Y register with a 0 or some other value and then load the A register or a memory register with a value to be used for a comparison. All right. After that is done, a conditional branching instruction is used to tell the computer what P register flags to test and what to do if these tests succeed or fail. This all sounds very complicated, and it is. Actually, I don't think it is. I think they make it sound a lot more complicated than it needs to be, because when you need to like compare something, you kind of know what you're trying to compare. You know, like here, you got the X thing, right? So you got X incrementing and you want to compare it with the number 23. So which one are you going to use? You can do like, you got branch if equal or branch if not equal, right? So you kind of have to choose how you want to do it. All right, where was I reading? And it is. But once you understand the general concept of conditional branching, you can use a simple table for writing conditional branching instructions. Here's one such table. Oh my God. Yeah, so this is saying like, hey, if you're doing it with a value or an address, then you're going to use the accumulator, right? And if you're doing it with a value, then you put the number sign in front because it's a value. And then if you're doing it with something that's in a memory address, you put a dollar sign. And here it's saying same thing with the X register, same thing with the Y register. So I really don't think it's that complicated. Let's just skip all of that because I think it'll just make sense naturally once we start using it. Assembly language loops. How much longer do we have here? This is my ADHD. Oh my God. Oh my God. Page 128, and we were on like here. So we got about like 10 more pages. Assembly language loops. In 6502 assembly language, comparison instructions and conditional branch instructions are usually used together. What are they saying here? Comparison instructions and yeah, obviously. If you don't compare, then it means you just want to jump no matter what, and that's probably less common than to basically do a loop or a jump based on a condition. In the sample program called the visitor, the comparison instruction CPX and the branch instruction BNE are used together in a loop controlled by the incrementation of a value in the X register. Each time the loop in the program goes through a cycle, the value of the X register is progressively incremented or decremented. No, it's only incremented in our program though. And each time the program comes to line 200, the value of the X register is compared to the literal number 23. When that number is reached, the loop ends. The program will therefore keep looping back to line 170 until 23 characters have been printed on the screen. Then in lines 220 and 230, we'll open your computer screen, clearing it in the process, and we'll print the string that has been transferred to the text buffer on the screen. Finally, at line 240, the program will go into what's known as an infinite loop, cycling back to the same jump instruction over and over again, and doing nothing else until you push the break key or in some other way halt the program. And that's infin for infinity, jump infin. Why use a buffer? Before we move on to our next topic, improving the visitor program, it might be worthwhile to answer a question that may or may not have occurred to you. The question is, why use a text buffer? Why not just print the text in lines 100 to 120 directly into the screen without moving it first into a buffer and then out again? Here is the answer to that question. Text can be loaded into a buffer in many ways, from a keyboard or from a telephone modem. I want a modem now. Do you think like if we had a modem, we could actually like call someone with it? Are there like still numbers you can call with a modem? I'm actually not sure that I could hook a modem onto like my phone system because it's all digital. I don't know how that works. For example, as well as being loaded in as data directly from a program. And once a string is in a buffer, it can be removed from the buffer in just as many different ways. Another advantage of a text buffer is that you can load it into RAM, note its address, and use it from then on whenever you like. A buffer can therefore serve as a central repository for text strings, which will then be accessible with great ease and in many different ways. Which means that it's kind of weird. Like, we have text here, right? In the text line. Why don't we just use the data here instead of moving it to a buffer? Why are we just moving this to another place? It's already here. Why don't we just load it into the right place? You know what I mean? Do you want to try that? Because we're putting it in text buff, right? Text buff is 5041, right? 5041. Oh crap! I did not mean to do that. I hit reset by accident. They need to be in video RAM probably. You can only have your data in ROM. Oh, so the byte stuff can only be in a special area? Right, so like what I'm wondering is what if I change this here to the other address, 5041? What if I go, oh, I can't go up? Why can't I press up? Anyway, I can't change it. So what if I go 80, 5041, right? So this will put it in 5041. And then why don't I put this? I don't know. Can I do it twice? Can I do like 130 and then do it again? And put it at $0600? You think this will work? So now it looks like this. 5041 for this code. And then 130 here. Let's see if the assembler lets us do this. Let's do that again, but this time I want to stop it. So 5041, yeah, that's fine. But notice here, it's putting it, it looks like it's putting it in address 5041, right? Yeah, you see 5441. And then I make it 600. It looks like it switches, you see? Now it's in 600. But the problem is, the code should no longer have to do this loop. So I think that means that I can basically clear all these lines. Oh no, I want 220. So, like, I don't even need 160, right? Probably I don't need 160. Yeah, I don't think I need 160. So there we go. We assemble this. And how did we run it again? It was like... Shouldn't it be G600? No, it was not G600 because it didn't, we had some byte stuff in there. So we had to skip over that. But now I should be able to just do G600. So let's see what happens when we run this. Hopefully I still have the other code loaded in. Look at that. Doesn't it seem like it still works? So, I think it works. So this whole example is sort of contrived. I've optimized it. All right. I'm gonna write more letters to the editor. All right, let's try to understand what's going on here. I am the leader, you fool! Okay, I don't see what this guy now has any... These medieval guys have anything to do with the inspector guy coming to visit the vampire lady. Like, guys, help me understand it. All right, improving the visitor program. Now we're ready to make some improvements in the program called the visitor. Yeah, just remove a whole bunch of lines like I just did. That's the improvement. I think once I was working with a guy and he wanted to optimize his code, and literally I just removed a whole bunch of code and it still worked. I was like, oh my God, it was like so perfect. But it's a little humiliating, you know? You don't want to like seem like a jerk, but what do you do when you remove someone's code and you're like, okay, now it's just a lot better? Not that the program doesn't work, it does, but it has certain limitations, and some of those limitations could be removed quite easily, as they have been in this new program which I've called response. Response is quite similar to the visitor, but as you will soon see, significantly better in several ways. Oh, look, they have a string here. You didn't need to put the byte thing in there. All right, so let's code this up, right? And I hope you do. You can type it into your computer's memory. All right, let's do it. First, let me just do a hard reset. So we have everything cleared from memory. That's Shift F5 if you're using Altera. Do you guys hear the little like click click noise from the Atari? So we're gonna start this. I have an Azerty French keyboard, so it's like so annoying that I have to press Shift to do like so many things like number signs, all the number stuff. I have to press Shift. 50401. I'm so bad at typing stuff, like, especially when it's abbreviated. So please help me. Someone helped me last time and it was like a lifesaver. Nine B. Two spaces here because now we're using an actual sort of opcode. It's a compiler directive. It's saying to start our code in memory address, store the code. Hey, I'm going to remember this time. We need to give it a compiler directive called opt-obj because this tells it to store the code in memory after it's assembled it. I'm getting a lot of messages, but nothing important. All right. Where were we? 100. 110 is nothing. 120 text is a label here, so only one space. Dot byte. I can't type lowercase. Is there a way to type lowercase? I don't know how to do it. Any of you have Ataris know how to type lowercase? RSPONS. Response. Response. 160. So here we're loading the X register with the number 0 directly. Oops. We need two spaces here for load X number sign 0 because it's an opcode. Then 170 is the loop. That's a label, so only one space. 180, load the accumulator with whatever's in text, address, offset by X, kind of like what we did in the old code. Uh-oh, I made a mistake. Someone said I can press up and retype it, except my up arrow key does nothing. So I don't know how to do that either. 180, 190 is store into the text buffer address offset by X. So we're just moving stuff. Store whatever in the accumulator into the text buffer address offset by X. 200 compare. Oh, now we're using compare instead of branch not equal. Right? Compare 9B. Okay, so whatever's in the accumulator, we're checking if it's equal to 9B. And remember 9B in line 80 here is the end of line character. So it's basically saying if the accumulator, compare what's in the accumulator with the 9B number, right? And then it says if it's equal to that number, then branch to fini. Are they French? And otherwise, increment the x, register. I did it again. I typed the same line number twice. Increment x, line 220, 230, jump, jump to loop. So we're just looping here. And 40 is the fini label. 250 is jump subroutine, open screen. And then 260 is jump subroutine, print line. And then we're going to come back, and then this is infinity. Jump infinity. The last code we just did this in one line. It was like infin space jump infin, but for some reason I guess it's just prettier to make it like this. Let's save this. And this is called response. Just response. Yeah, let's store it as response. Response dot source. List will print it, right? Yeah. Okay, so it saved it. So let's look at the assembled stuff again. So we have these are not, this is not code, these are just like constants that it's setting. And then we're saying here start with memory address 650. So here the text starts at 650, but our code starts in 66B. Yeah, our code starts in 66B. And it ends in 681. So let's write that down. 66B to 681. Ah! I just reset. Why am I so... But we've assembled it, so it's in memory. We just have to load that print screen file so we can load, print SC1. Okay. All right, so now we have this. And now we should be able to run this in bug 65. The program was in 66B, right? So let's look at that, 66B. Yeah, it looks like there's a program there, and in 600 it should look like take me... Wasn't it in 600? I'm a little confused. Oh, 650. It was in 650. Display 650. Yeah. I am the. You see, so the code is in there. I am the leader, you fool. So how do we run? If you want to run the response program, and I hope you do. Yes, we do, right? You can type it into your computer's memory right now. Since it calls the same subroutines that its predecessor did, you can assemble it and run it as soon as it's typed, provided you still have the program called print screen is loaded into RAM. To run the response program, you can go debugger, should be able to run 66B, right? So let's do that. G66B. Almost. Well, that's interesting. Why did that happen? Response.source. Where did we go wrong? Maybe I typed the program in wrong, right? Response. I didn't type it right. Right. Let's list this. I guess let's list it slowly and compare it. Response text buff equals 5041, open screen 5003, end of line on 89B, 95 option obj, 100 0650, text.byte I am the leader you fool, 140 RSPONS, 160 load x number 0, 170 loop, load accumulator text comma x, 190 store text buff comma x, 200 compare number sign $sign 9b, beq branch equal fini increment x, 230 jump loop. Yeah, that's 170. 240 fini. 250 jump subroutine open screen. 260 jump subroutine print line. 170 infinity. 280 jump infin. That seems correct, right? I feel kind of bad, like it should work. Starting to piss me off. Go 66B. You guys see that? It didn't go all the way. Aha! It's expected. I don't know why it didn't work the first time. But it didn't print all of it. Provided that you've typed and assembled it in accordance with the suggestion that I've provided, even if you've followed the instructions through, you'll still encounter one small problem. Only the first 23 characters of the string, I am the leader you fool, will print on your computer screen. That's because the text buffer we created in the program print is only 23 characters long. The flaw is easy to remedy, but before we fix it, it might be a good idea to save response on a disk in its both source code and object code version. All right. We've already saved the source, so I'm not going to deal with the object. Fixing the print screen program. Now we're ready to lengthen the text buffer used in print screen program so that it will print its complete message on your computer screen. To lengthen the print buffer, just put your assembler into its editor mode and load the program source code into your computer's memory. Then you can change line 70 from bufflen equals 23 to bufflen equals 40. When you've made this change, you can save the amended source code under the file name print_sr2, assemble the program, and save the object code under blah blah blah. When you've saved your programs, you can reload the response program, run it with this instead. This time you should see the full string on your video screen, but unfortunately you'll now notice something else wrong. After the line, I am the leader you fool, you'll see a line of little hearts. How did they get here? All right, let's try to do this first. So we get out of this. We go back to the Max65 compiler. And we load our parent screen1.source program. We can list line 40 to 100 here, and bufflen is 23. So they say change it to 40, so we're going to do 70. Bufflen is equal to 40. Is that how it looks? I think that's how it looks. And now when I compile it, bufflen is 40 now, which is hexadecimal 28. That looks good. Let's save this program as print screen2.source. We've already assembled it, so now all we should have to do is just rerun our previous program, which started in 66B. So let's try that. Go 66B. Oops. I wonder why it does that. Go 66B. It's still not happy. Maybe it's the order that I'm doing things? Let me try seeing if I compile the visitor program, if it'll like work. Was it 2? Visitor 1? I forget what it's called. No, we don't want visitor, we want a response. Crap, was there a response too? This one has what did this change? I think this is just response. Alright, let's try this. G66B. Okay, now we see it. Maybe it's the order. Maybe I can't compile the first program second. I don't know why that would be though. Alright, I am the leader, you fool. Now we have the hearts. We did this. We did all this. Little hearts. How did they get there? I'll answer that question in just a moment, but first let's take a look at some of the differences between the program called the visitor and the one called response. A better routine. Gotta finish my coffee. From a technical point of view, the response program is better than the visitor for several reasons. The most obvious difference between the two programs is the ways they handle the text strings. Yeah, because we were using the we just put in a literal string with quotation marks. In the program called Visitor, we used a text string made up of ASCII codes. In response, we used a string made up of actual characters. That made the program much easier to write, and it makes it much easier to read too. Another important difference between our newest program and its predecessor is the way the loop is written. In the program called Visitor, the loop counted the number of characters that had been printed on the screen and ended when the count hit 23. So it's like if you did a string length first and you knew it was going to be 23 characters and then you loop to string length, right? But instead here, it's kind of doing it like the way C does. How does C do it? It's like it's looking for the null character, right? So it's basically going through a string, each letter, until it finds 0, and then it knows it's the end of a string. So we're using EOL as the end of a string, so we're looking for that. Now that's a perfectly good system for printing text strings that are 23 characters long. Unfortunately, it isn't so great for printing strings of other lengths. So it isn't very versatile. It's not a very versatile routine for printing screen characters on a screen. Testing for a carriage return. The response program is much more versatile than the visitor because it can print strings of almost any length on a screen. That's because it doesn't keep track of the number of characters it has printed by maintaining a running count of how many letters have been printed on the screen. Instead, each time the program encounters a character, it tests the character to see whether its value is 9B, hex 9B, the ASCII code for a carriage return or end-of-line character. If the character is not an EOL, the computer prints it on the screen and goes on to the next character in the string. If the character is an EOL, the EOL is printed on the screen and the routine ends. And that's that, except those pesky little hearts that we encountered when we ran the response program. Now we'll take another look at those hearts and see what we can do about them. Yeah, I have no idea what those hearts are. I see, because we made a string. We didn't like null it out, the text buffer. The hearts are there because the text buffer we have set up for our visitor and response message is now 40 characters long, longer than either of our messages. And the part of the buffer that's left over is filled with zeros, as empty memory locations in computers usually are. Then why the hearts? Well, in a ASCII character code that your Atari uses, a 0 does not equate to a space. Instead, it equates to a heart-shaped graphic character. The ASCII code for a space is hexadecimal 20 or 32 in decimal notation. Just look at ASCII character string in the visitor and response programs. You'll see that the spaces in the message "Take me to your leader" are indeed represented by the value 20. It is possible, of course, to print messages on your Atari screen without strings of hearts appearing after them. What you have to do is keep the hearts from appearing is clear your text buffer, or more accurately, stuff it with spaces before a program runs. So here's it that will clear your text buffer. Should we try to write it ourselves? Where was our text buffer? It was in 650, right? Let's take a look at it. That was response.source. Yeah, you can see it's in 650 is where the buffer begins, where the text begins. And then we can just like clear it out. So let's try to write a program that does that, huh? Do we know enough yet? So let's do 100. Oh, where do we write our program? Let's put our program in 66B like the other one. We'll run our program first and we'll load 66B. But in that case, it should be zeroed out, right? Let's see if this works. Opt to do this, and then we store it in hexadecimal 66B. And then we want to set our register to our X register to be 0, right? What is that? Load X 0. And then we want a loop. have an alarm that goes off at 9 p.m. just to ask me if I've eaten, because sometimes I just don't remember to eat. And then I like start falling apart and I don't know why. And I'm like, oh, I'm sick. Sweetheart, why am I sick? What's going on? And then I try all these things and I realize, oh, I just haven't eaten. Okay, so now we want to copy the number 0 into this address. So I guess we can just load into the accumulator the number 0, right? This is probably a better way to do it, maybe. And then we can just store that into it's 600, no, 650 offset by X. So that'll put a 0 there. And then we check if we just stored that there. Load accumulator. Do we increment the accumulator first? I want to know how I think we normally increment the accumulator first, right? No. I think here... No. We want to do compare... What was the compare with X thing called? CMX? CPX. Compare X with 40 because we want to clear 40 characters. And we say if it's not equal to 40, then we go to loop. Branch if not equal, go to loop. Otherwise, we increment X. Oops. Compare to 40. I think I need to increment it after I store it. Otherwise, it'll never increment. So it looks like this. Increment X, compare X to 40, and then branch to loop if it's not equal. Otherwise, I'm done, right? I think I can just end. So let's try to save this as clear.source. No, it's not enter, it's list. I almost really screwed myself. List d2 clear.source. So this will save, it'll save it, right? Yeah. And now let's try to compile and see if it compiles. Yep. So here it starts in address 66B and it ends in 677. And it's going to clear address 650. So let's see if this works. Bug 65. My code is in 66B. There's our code. And 650 is the buffer, right? I am the 50, 1, 2, 3, 4, 5, 6, 7, about 8. I am the leader. Oops. You fool. And then you see after fool it has stuff. So that's at 668. You can see that it has garbage in there. And after I run my program, it should no longer have garbage in 668. Like all of this should be clear. So let's try running it. Go 66B. Oh crap. Maybe that's how it goes until you tell it to break. Now let's display 650. It's all empty. 668 is all empty now. But in my code where it's 66B, where's my code? Why did it clear my code? Maybe it's too long. Anyway, let's try going back and now loading the response program. Max 65 420. We load that program, which is enter the. Actually, let's load the print screen just to be sure. We assemble this. Then we load the other program. Okay. Ay, ay, ay. Alright, so I failed. Fool, question mark. Oh, it's really close where our code begins and the other stuff. Oh, does it overlap? It might. Anyway, let's see what they do compared to our code. Okay, so they have fill load accumulator with fill character, whatever that is, right? Load x with buffer length. Oh, here they're decrementing x. I'm incrementing x. So this is 40. Start. Decrement x. Oh, they have return to subroutine. Maybe that's better. Store accumulator text buff, which is the same number I have here, right? Comma x, branch not equal, start. So it's very similar. Oh, I put in 0, which is the exact wrong character. I need to put in 23 for the fill character, which is the space. Or 20, right? I'm so stupid. That's why it'll print hearts anyway, because the whole point was that I wonder, how do I go up? So maybe I should have done it like this too. So then they're going to have to call fill to start this thing first. Jump subroutine fill. Yeah, and then it jumps to fill. Yeah, that makes sense. So let's try that without looking. Let's start that over again. Woo! We can do this. Wait, is it visitor pro? No, it's the response program that we're changing, right? Oh. Incorporating it into your visitor program and response program. Why are we doing it into visitor? Oh, here's response. All right. Let's try. It's hard writing assembly because you can't just like use an IDE to do things. It's kind of crazy how much harder it kind of feels because of that, you know? Oh crap. I am an idiot. Alright. I meant to press F8 to stop it. Okay, so we're gonna need a new constant for bufflen. So I don't think there's anything in here for that, right? Oh, here. So we'll put it under like 65. Bufflen is equal to 40. 65 bufflen is equal to 40. Okay. So now we have our buffer length set to 40. Do we need anything else? Oh, we also need a character that is the clear character, the fill character, right? So let's put that as 66. Fill character is equal to, was it 21? Or was it 20? I'll assume it's 21. We can look and fix it later, right? Okay, so we have that in here. And now we want to add our code somewhere in here. They put it pretty low, like pretty high in here. Like we'll call it fill. So that's our label for our fill code. And in the fill code, we're going to load the X register with the value bufflen, right? That was from the constant that we made earlier. I think that's right. And then I guess we want to load the fill character into the accumulator. I don't think we want to loop. We don't start the loop yet because the fill character is always going to be the same. So we can just load that into the accumulator. What's it called? Fill character? I think just fill ch, right? All right. And now we want a loop, I think. So 1330, we can say f loop. And in here, we basically store the accumulator into the whatever, what's it called? The buffer text buff. That's what it's called. Text buff comma x. No. Yeah, it's text buff comma x, right? Yeah, I think so. And then that'll basically put it in the last character in the text buffer. So we're kind of filling it right to left instead of left to right because we're starting at 40. And then we want to decrement the x, and then we want to compare that branch if not equal to 0. No, branch if 0. How do you do branch if 0? Here we go. Compare x 0. Is that what we do? No, I think when we decrement x, it's already going to check if it's going to set the flag, right? So I think we can just do branch if not equal. I don't know. We'll have to check this. And we branch to f loop. Otherwise, we return from subroutine, right? Does this look right? I feel like I forgot stuff. Let's take a look. Let's compare how we did. So we have fill, load. Okay, so this doesn't really matter what order it is. You see, like they did LDX bufflen first, second, but I did it first, and then they do LDA fill CH second, whatever. We split. Start. They called it start. I called it F loop. Decrement X. Oh, so they decrement first. Then they do store text buff X. Branch if not equal to start. I don't think the order there matters between decrement and oh, it does, because yeah, it's mine is wrong because it's going to, it's like the length minus 1 issue. The length is 40, so we want to start with minus 1, so we should decrement first. They're right. But otherwise the statements were correct. Text buff comma X. Start, they called it start decrement, store, branch not equal, floop. And the branch not equal, I don't think that is not affected by the store command. So it's basically looking at the decrement X command and checking if it is 0, right? All right, let's see here. This program is quite straightforward. Using indirect addressing and the X register countdown, it will fill each memory address in a text buffer with a designated fill character of fill CH. Then the program ends. The subroutine will work with any 8-bit fill character and with any buffer length up to 255 characters. Later on in this book, you'll find some 16-bit routines that can stuff values into longer blocks of RAM. You can use this routine by incorporating it into your visitor program. Let's do it first. Let's make sure that, oh yeah, we have to do the jump subroutine. But let's do it first to our response since that's what we're playing with. So let's list it. Text buff, open screen. Then we have bufflen 40, fill character 20. Oh, it's 20, not 21. So our 66 fill CH should be 20. Okay, fill CH is 20. We fix that. 9B. 650 text byte, blah, 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 load x0, that all looks right. I think all of that's the same. And then here we have our fill, we have this, start, return subroutine. We need the part where we fill first, no? Jump infinity. So where do we actually go to fill? We're never calling fill here, so I don't know how. This looks wrong, right? You see here in the visitor program, they do jump subroutine fill right in the beginning, right before their loop. We don't jump subroutine fill. Yeah, so I think they made a mistake here. We need, right before we do this loop on line 160. Oh crap! I didn't save my code. I pressed F5. Oh my god. Autosave. God, how many times has that happened to you guys? Oh my god. I don't think we lost a lot, right? I think we did lose some. We lost some, guys. Oh my god. Well, what can you do? We can cry. Bufflen equals 40. 66. Fill character equals 20. We did that before, right? And then I think what I was saying is in line 155 we should do jump subroutine fill. Otherwise we'll never start it. And then yeah, I sound so sad, right? I don't remember what I wrote exactly, but it was like, I had it the other way, so I'm going to keep my stuff. I think just to show that it doesn't matter. And then here I called it F loop, right? And 340, I realized we should decrement X. 350, oh no. This needs to be 2 characters, decrement X. 350, store the accumulator, which should be the fill character, into the text buff, comma, offset by X. And then 1360, branch not equal to floop. And 1370 returns to subroutine. Let us save this. resp2.source. Okay. Let's try to compile this. The code starts in 66B and it ends in 691. All right. So that should be all assembled, although we didn't assemble the first program, so we should do that. Let's do that now. Enter D2 print screen 2 dot source, is it? hey, please no username. Yeah, I think this was the right one. We will assemble this. And then we'll also load our last one just in case. It was called resp2.source. And we will assemble that. And now we'll run it in our debugger. G66B. I am the leader, you fool. And look, it has spaces. It works. I'm pretty sure that wouldn't have worked if we just did what they did because they never call the fill subroutine. I feel like I'm trying to convince you guys I'm right. They screwed up. They needed to call the fill subroutine here somewhere. So good job on us to figure out that it's busted. But no more hearts. When you have both of these improved programs safely stored on a disk in both their source code and object code versions, you can run them and see that all of our difficulties with our text buffers have now been resolved, and that brings us to our next chapter in which you will learn how to call assembly language routines from basic programs. Yay, guys, we finished chapter 7. Congratulations, everyone. I hope you enjoyed that as much as I did. Well, I really enjoyed it except for the part where I deleted my code. Like, that was painful, right? But yeah, that was a lot of fun. We learned how to basically mostly print characters with assembly, to do loops, to do branches. There was one part that was still a little confusing, was that BNE. Let's look it up because maybe it is useful to kind of just remember what it says here. Branch if not equal to 0, that was the BNE we used, right? And what was complicated is this. So I was making fun of it and it bit me in the ass. That instruction, BNE loop, which means branch to the next statement labeled loop if the 0 flag of the process status register is set. This instruction uses what can be a confusing convention. If the register 0 flag is set equals 1, if the 0 flag is set equals 1, if, oh, here it is. The 0 flag is set if the result of an operation that has just performed is 0 and that 0 flag is cleared. So when we decremented the X register and it became 0, then basically the 0 flag was set. Branch to the statement labeled loop if the 0 flag is set, right? So we sometimes do have to think of BNE loop as branch if 0-bit is set. Because when we do decrement X, we're not really checking if it's not equal, we're checking if it's really 0-bit is set. So it's kind of actually a bad thing, right? So branch if the 0-bit isn't set, and decrement X will set the 0 flag. Where do we learn about decrement X? Somewhere? Probably somewhere else, but I'm sure it sets the 0 flag when it gets to 0. Alright, well, this will be loaded as a VOD, so if you're watching this on YouTube, then please do like and subscribe if this was fun. There's a whole playlist for all the other chapters up to this. So if you're like, hey, you know, looks cool, but I don't know what we're doing, go back to the first one, follow through, read the book if you want. There's all the links, all this stuff is available to you. I would love to hear that it's working for you guys. To the person who gave me the F8 hint, thank you so much. That was so useful. I now need the hint of like, how do I go back up with Altera? Like, I don't know how to like go back up and down with Mac 65 stuff. Like, how do I go up and down? So if I do 10, you know, foo equals 3. How do I go back up to edit that? That's what I need to know, and then I'll be in good shape. So yeah, that's it. Thank you so much for hanging out with me. Hope you enjoyed that. Thank you all. Thank you all. Bye. And we'll continue later. I also do videos on like other things like Nix and Haskell and COBOL. Yeah, we got to do COBOL. Oh my God. COBOL's starting to stress me out. Like every time I get ready to do COBOL, I'm like, okay, it's hang on tight. It always feels like such a fight, you know? Maybe it'll get better. Maybe I'll learn to love COBOL. But yeah, oh, yeah, I'll do it next time. Thank you all. Bye.